Yeah.
Okay. Our next speaker is Mikhail Shifman from the University of Minnesota. He's going to tell us about this mysterious supersymmetry and how it helps us to understand our world.
Okay, thank you very much. Can you hear me, by the way? Is it okay with the microphone? Okay, so my task is a little bit facilitated by Nick because he introduced some notion which I'm going to use in my talk. This is will be my pointer. Okay, I'm going to present here a very general and by and large non-technical introduction to the issue of supersymmetry, which preoccupied theorists for the last 35, 37 years. And it's a very deep concept which will hopefully be finally confirmed at LHC in a year or 2 years from now. But at first, let me try to ask the question, what is supersymmetry? And I will try to answer it in some general terms. Supersymmetry, if it holds in nature, is a part of the quantum structure of space and time. We got used to the fact that in everyday life we measure space and time by numbers. For instance, the linear dimension of this institute is, let's say, 40 meters. And then we can measure the area by squaring this 40 meters. We end up with 1,600 square meters, and we say the time now is 235, and so on. Numbers are, of course, classical concepts, and that's why we can square them or cube them and have the volume of this institute. And our basic way of thinking about space and time has not been affected by various physics revolutions which occurred 100 years ago. And as we know, this was Einstein's relativity and special relativity, which appeared in the very beginning of the 20th century. And then 20 years later, we saw the birth and then the rapid development of quantum mechanics. Everything was quantized. But the notion of space and time as being represented by classical numbers was not affected. Supersymmetry, if and when it will be discovered, will totally change this, because space and time will acquire some other dimensions which are totally quantum. They are not classical. These dimensions are referred to usually as the fermion direction of the space of time, and they are described by Grassmann numbers. The Grassmann numbers are subject to all theorems of regular numbers, conventional numbers, with one exception. If you have two Grassmann numbers, they anti-commute with each other rather than commute. And this is the basis why we call these dimensions fermion dimensions, because anti-commuting of fermion operators is the basics for the introduction of the Fermi statistics. In particular, if you have only one Grassmann number, its square is 0 because it anti-commutes with itself. If we have four dimensions, four regular dimensions, three spatial dimensions, x, y, z, and t, then the minimal extension of the superspace which you can make will consist of one complex Grassmann spinor. Each spinor has two components, and it is complex. Therefore, we deal here with four Grassmann numbers. If we can have also 8, 16, and 32 Grassmann numbers, such supersymmetry is called extended. As I mentioned, these fermion dimensions are not measurable by ordinary numbers. And in fact, if you try to think what is the reflection of the existence of the fermion dimension in the space of time, how can our perception be affected by this? The only way we see them is kind of indirect way. We see them through introduction of new particles. Okay, here is an artist view, you know. These are regular dimensions, and fermion dimensions we can neither see nor feel, but they somehow if you look here, you see that somehow we can feel it indirectly. So here is what is depicted here is intuitive representations of a field theory without for a field theory with the particles which have no spins, and the field theory with the particles which do have spins. You know that you can view field theory as an infinitely many oscillators occupying every point in space. You have discretized, at least in your mind, discretize the space and put a quantum oscillator at every point of space and then connect them by harmonic forces, by springs. And then if you have a particle of spin 0, you can view it as a wave propagating along this chain. It is a one-dimensional chain for one-dimensional field theory. For 3 spatial dimensions, it has a 3-dimensional structure. Now, if you have a particle with spin like an electron propagating along this chain, along the space, then you have to visualize it putting a spin, a possibility of rotating every quantum oscillator at every point of space-time, and then you can have 2 types of waves: oscillations of the oscillators and a spin wave. And this combination of these 2 things creates a particle propagating with spins. Now, as I told you, supersymmetry would mean introduction of new fermion dimensions, and then particle vibrating in these new fermion dimensions would look in our detectors like new elementary particles, but they will have typically different spins. For instance, if our original particle of the world is boson, like for instance the Higgs boson mentioned by Nick, its superpartner will have spin 1/2. It will be what is called Higgsina, and it is a fermion. Okay. Here is the summary of what I have said. If supersymmetry is varied in nature, this would mean that for every particle that has been found already, there are mirror particles that are identical in all respects except for their spin. Bosons of spin 1, the photon, W, and Z, and gluon have spin 1/2 partners called the photina, wina, and gluina. And on the other hand, the fermions of spin 1/2, leptons and quarks, have spin 0 partners called the leptons and quarks. Here are a few other facts about bosons and fermions. And if you remember the textbooks, then you remember that bosons and fermions in our life play a very distinct roles. Fermions are the building block of matter. All what they see around is matter, and us also, we are built from matter. And all matter is built from fermions. For instance, here you see a proton, and the proton is built from, or no, it's not a proton, it's rather a nuclei, and the nuclei which is built from 2 protons and neutrons, which are fermions. Each proton is built from d quark and 2 u quarks. These are fermions too. And this is an electron, a lepton, which makes this atom neutral. There should be 2 of those. I don't understand why it is 1. Okay, let's say this is an ion. It is positively charged, but it's a part of matter too. Now, spin 0 particles and spin 1 particles and bosons in general play a totally distinct role. They are force mediators. We know that the mediator of the electric force or magnetic force is the photon. It has spin 1. And there are other mediators. For instance, the mediator of the strong force mentioned by Nick is gluon. Here it is depicted. It's a thing which combines and quarks binds them together inside the proton. It also has spin 1. W boson, which mediates weak force, also has spin 1. And finally, we expect the discovery of the Higgs particle, which mediates mass interactions, and it has spin 0s. spin 0. Apart from playing such a distinct and not particularly similar roles, there is also the issue of statistics. We know that fermions are subject to Pauli statistics, and therefore they are extreme individualists. Absolute, I would say, individualists, because due to the exclusion principle, there can never be two identical fermions in one and the same state. They just don't tolerate themselves. On the other hand, bosons are extreme, I don't know, communists, let's say. They love huge ensembles, and they love to congregate together, and they love to repeat each other. The more identical bosons you have, the more other bosons want to join this ensemble, want to be totally identical to this. The probability grows. So the question is, given these two absolutely distinct positions in our world, supersymmetry tells you that there is a certain symmetry between bosons and fermions, and the question is, how can that be, and can that be at all? Can there be any symmetry between bosons and fermions? And since I'm talking here about this, you've already guessed the answer. The answer is yes. And the positive answer to this question has been bound remarkably in 3 different places, almost simultaneously, within 1 or 2 years from each other. And basically, the people who found the answer didn't know about other people. The first work on supersymmetry was due to Goldfund and Lichtman. It was done in 1970, published in 1971. This is Goldfund, who died some years ago, and it was in Moscow, and they obtained the first supersymmetry algebra, which I show, and also derived supersymmetric quantum molecular dynamics, the first supersymmetric for dimensional field theory ever known. Then in 1972, there were a paper by Volkov and Soroka, who laid the foundation of what is now called supergravity, and I will say a few words about this paper later. And then next year, there was the work of Julius Wess and Bruno Zomina. Julius Wess just died a month ago. And this was done at CERN, and their work, they came to supersymmetry from a different side, from the side of generalizing gauge transformations, not from the algebraic side. And their work signified the beginning of the supersymmetry revolution, because after they published, there was a group enthusiast at CERN and in London, Salam and Stratdy, who spread the idea, spread the world, and it went to masses. So the answer to the question, can there be any symmetry between bosons and fermions, is positive. Now I want to say, this is my personal opinion, but I want to make a conjecture and guess that in general public in the 20th century, this famous formula due to Einstein was kind of a cultural icon. You can see it not only in texts and public lectures. There are lots of T-shirts or mugs, or whatever. You can see it everywhere. That was the public perception of physics in the 20th century, the essence of physics, I would say, its core. Now I make a conjecture, which I would say would be especially true if supersymmetry is found within a year or two, that in the next century, the cultural icon of physics will be not this one, but the basic formula of supersymmetry. Here's the basic anti-commutation relation for supersymmetry, which was derived by Goldman and Lichtman. And I will explain a little bit right now why it took people so much time in order to derive this relation. First, I explained what stands here. P mu is the energy momentum operator. We know that in nature there are 4 basic conservation laws which are kind of sacred. You know that the energy is conserved, the total energy is conserved, and the three spatial components of the total momenta are conserved. So P mu is the energy momentum operator, which is an absolute conserved quantity. Now, for many years, people try to figure out whether there can be other conserved quantities with the Lorentzian indices. We know that there are other conserved quantities. For instance, the baryon charge is a conserved quantity, or the electric charge to that effect is a conserved. The total electric charge of the world is a conserved quantity, right? But the total electric charge is Lorentz scalar. Therefore, its conservation doesn't affect at all the geometric aspects of nature. It is a number, overall number, like the number of money in a bank, you know. If it goes somewhere, it not disappear, it goes to another bank. But if you take the sum of money over all banks, I mean, this is a conserved quantity, right? But it's a pure number, has nothing to do with geometry. When we speak of the, let's say, conservation of energy, which is the time component of P mu, it has to do with geometry, because we know that the energy conservation means homogeneity in time of things. So it is geometry. And there was, in the end of 1960s, there was a very basic theorem proved by Coleman and Majdula that other than the energy momentum, there can exist no other conserved quantities which have Lorentz indices. If they would exist, said Coleman and Mandela, this would lead only non-interacting objects, you know, only objects which don't scatter can have, let's say, other conserved quantities with the Lorentz index. Of course, if you have a sterile particle, say the square of its momentum is also conserved, right? Because it goes through, doesn't change anything. But if there is at least any interaction, then according to Coleman and Mandula, there couldn't be any conserved quantities of the type. This was a stumbling block, and people believed that this precludes invention of other conservation laws. And the first people who posed this question, whether or not it's true, were Goffin and Lichtman. And as I said, you already can guess that they did invent it. They found a loophole in this theorem. And the loophole was that, of course, Coleman and Mandula didn't assume that there can be conserved quantities which are fermions, which have spinorial indices rather than vectorial or tensorial indices. Okay, so what you see on the left, these are called supercharges. They are spinors, and therefore this is a representation of 1/2 0. This is representation 0 1/2 of the Lorentz group, and their anti-commutator forms the energy momentum operator. So roughly speaking, it's the square, it's a fermionic square root of the energy momentum. Okay? And it turns out that if you postulate this algebra and then start checking the Jacobi identities, the algebra closes, and moreover, you can write field theories which satisfy these algebraic relations, which are supersymmetric. In these field theories, you have boson and fermions, which are, in a sense, symmetric to each other. I will discuss this in a little bit more detail later. Now, why do I think that this is going to become a cultural icon? Just see the number of papers devoted to supersymmetry, even though supersymmetry, I remind you, is not yet discovered. There is only one, at most two rather weak and direct directions that it might be present in our world in some broken form. But theorists reacted, you see, fiercely. Even in spite of the fact it is not there, you see that the average number of papers devoted to supersymmetry now is close to 1,000 per year. If you take the total integral, I believe it's something about 30,000. There was some, you see some dip here around in the late 1980s, early 1990s. This is devoted to the explosion of string theory. where people moved away from field theory, from supersymmetry to string theory, but then it happened, but then this gap was closed, and now you see it goes this. The last number is not complete yet because the year 2007 is not yet finished, so it will go up. This is for comparison, by the way, the number of papers devoted to the large extra dimensions, and you see, although it caused a very big interest in the community, these numbers are not just comparable, neither in overall number nor, of course, in the integral. Okay, here are these partners which I mentioned. For instance, for electron, and the naming of the partners is rather peculiar. For electron, we have selectron. These are spin 0 superpartners, and for spin 0, we just add the letter S. For muon, we have smuon. For tau, we have tau. For neutrino, we have neutrino. For quark, we have squark. And the other way around. Let's say here we have W, which is, in our world, we know that a W exists, and the conjectured superpartner is spin 1/2. So if W is called W, its superpartner is called Wiener. If Z is called Z, its superpartner is called Zeno, photon, photina, gluon, gluina. Higgs, which is not yet discovered, but is expected to be discovered at LHC, is expected to be accompanied by Higgsiana, and so on. Okay, here is already, Nick already shown the aerial view of LHC. LHC, this is a big circle here. This is Geneva, and Switzerland, at the border of Switzerland and France. And the parameters of LHC are such that most probably, if supersymmetry is indeed present in nature, then with high probability it will be discovered at LHC, unless it is, we don't know, you see. We don't know what's going to happen. There are some contrived theories where supersymmetry doesn't manifest itself at the energies which are expected to be achieved at LHC. So although I say that most probably LHC will see it, maybe it won't. So now when I explained in general terms, non-technically, what supersymmetry is and why it connects bosons and fermions and in which way it connects it and how it can be discovered, let me try to ask another question. Why do we need supersymmetry? Why people publish 30,000 papers without direct experimental evidence that it is there? And the answer to this question is there is more than one answer to this question. I would say that the initial motivation for the explosive growth of research on supersymmetry, which happened, the supersymmetry, as I said, was discovered in the early to mid-70s, and before 1980 there were not so many people. Some basic theoretical work has been done, and here, besides the inventors of supersymmetry, I should mention a very important role of Salaman Strategy and Sergio Ferrara. But the explosion of phenomenological supersymmetry occurred beginning in the 1980s. And at that time, people realized and start thinking that supersymmetry might be important in explaining the very important problems of the world, namely the so-called hierarchy problem and the cosmological term problem. Let me remind you what is a hierarchy problem. If we look in our nature, then it seems, at least at the moment, we don't know the future, but if we look at the moment, it seems that the only fundamental constant, the true fundamental scale of nature, is the Planck mass, which is the inverse square root of the Newtonian constant. And it's a very huge parameter, 10 to the power 19 GeV. The corresponding length scale is 10 to the minus 33 centimeters. It's a very small length scale. At the same time, we know that this is not the scale of things we are built of. Proton has mass 1 GeV, and W boson has mass in the ballpark of 100 GeV. If you take electrons, they're lighter still. So it is not clear. There are two issues here. It is not clear why and how, out of the fundamental scale, which is huge, 10 to the 19th GeV, nature chose to operate at a much lower scale. You see, there is a gap of 17 or 18 orders of magnitude here. This is one aspect of the problem. And another aspect, even if you originally fine-tune this mass gap, and then start including radiative corrections, generically radiative corrections are not stable. They don't maintain this separation. And they tend, say, quantum loops tend to drag the theory up to its fundamental scale. So this is called the hierarchy problem, because there is a huge hierarchy between the scales we live at and operate with and the fundamental scale of nature, which is related to gravity. Another, even a huger hierarchy is probably related to this one, but it's not directly known how it is. It's the issue of the cosmological term. You know that in Einstein's equation, in principle, you can introduce the so-called lambda term or cosmological term. And again, the natural scale for the cosmological term would be Planck mass to the 4th power, okay, which is to the 4th power almost 10 to the 80 GeV. While in nature, for many years, it was believed that this is the same, the cosmological term is the same as what is now called dark energy of the vacuum energy. The energy of the density of energy in the space far away from any objects like galaxies. If you go somewhere far away and distorted by gravity, you would feel it, okay? For many years, it was believed that it is exactly zero. Until recently, it was discovered that it is not zero. It doesn't vanish, but it is extremely small. And if you compare the measured value of the vacuum energy density of the cosmological term with the one which would be natural, which is 10 to the 19th to the 4th, the difference between these two numbers is 128 orders of magnitude. Okay, it's the largest error theory makes against experiments known so far, because natural theoretical prediction would be 10 to the 76, and if you compare it to what is measured, it's 128 orders of magnitude, okay? So how supersymmetry might help in this respect? In fact, it was noted already by Lichtman, I believe, in the 70s, that if supersymmetry were exact, then this epsilon vacuum would be exactly zero. Why it would be exactly zero? That's because the contribution of the bosons, which is positive, bosons produce a positive contribution to the vacuum density, to the vacuum energy density, and fermions, because they have Fermi statistics as they should, produce a negative contribution to the fermion, to the vacuum energy density. If supersymmetry is there, then these two contributions exactly cancel each other, and then we would get zero, which would be good. In fact, maybe I should mention that quite recently I wrote for some, I read for some reasons an old lecture of Pauli, which was published in 1948, and here he makes in passing this remark. Already at that time, he was puzzled by the cosmological term, and he made the remark that for free fields, if there is an equal number of bosonic and fermionic degrees of freedom, the cosmological term is exactly zero. of course, at that time, he didn't know what to do with interactions, but supersymmetry takes care of this statement with all interactions included. Another reason why supersymmetry will be, so the first reason is efficient decoupling of high energies from low energies. Okay, another reason which came into limelight a little bit later was the fact that supersymmetry naturally predicts very good candidates for cold dark matter. We know now that 25% of our world consists of cold dark matter. Roughly 75% consists of dark energy. This is here. 25 persists of cold dark matter, and whatever we can see without telescopes or in any other way is peanuts compared to these two sources. So supersymmetry contains a very good candidate neutralina for cold dark matter. Of course, as I said, everything in this world comes at a price. You cannot improve things without introducing some negative sides. There is no such thing as absolute perfection. And the price we have to pay for these two explanations, there are two prices. First of all, superpartness. We double the number of particles. We predict that there are twice larger number of particles than the C. And these superpartners are still to be discovered. This is not the end of the story, however, because supersymmetry, as we know, is not exact. We have electron in nature, we don't have selectron. We haven't seen it so far. And the vacuum energy density is not exactly zero. It's slightly different from zero, which also shows that supersymmetry cannot be exact. In exact supersymmetry, this would be exactly zero. Okay? So we have to think on that and to work on that. Now I should mention another thing, another reason why supersymmetry is needed. And this is very good because let's assume that there is a total disaster. LHC does not discover supersymmetry. On one hand, all those 30,000 papers or so which have been already published, in a sense, go into a waste basket, right? Supersymmetry is not discovered, it goes. It's not quite so. Because there is another side of supersymmetry which is maybe not as global and as fundamental as a new dimension, a new fermionic dimension in a space-time, but it is very useful. Supersymmetry proved to be an extremely useful tool for solving otherwise unsolvable problem of strong coupling dynamics. And in fact, Nick mentioned one of these most fundamental problems, and it is not a conjectured problem. It's for real because QCD is a very robust and down-to-earth science which describes matter, right? And matter is, we know it is here, right? So, and it is very unusual science in terms of dynamics because it tells you that interaction between blocks of matter grows with distances rather than becomes weaker, and this is very unusual. And it's very hard to deal with theoretically because the coupling is strong and none of the known methods is really very useful in approaching this problem. It turns out that supersymmetry might help, at least in some aspects of the solution, and it costs nothing compared to every effort, we invest in LHC because it costs just the cost of paper and pencil for theorists which can use it without further effect. And I should mention, and if I have a little bit of time, I will elaborate on that. Enormous progress has been made in understanding of strong gauge dynamics using supersymmetry since mid-90s. Okay, I will probably have mostly to skip this graph. I mentioned to you that if supersymmetry is valid in nature, it will have to be spontaneously broken. And the mechanism of spontaneous breaking of supersymmetry is the hardest theoretical part of it. And I wanted to explain what spontaneous supersymmetry breaking is, but I have no time, so I'll just make one small remark. You know, when you broke ordinary symmetry, like for instance charge conservation, you spontaneously broke, not explicitly but spontaneously. As a result, you have a massless particle. For instance, here you see magnetization vector, and if your sample is magnetized, then you have a gapless excitation which is called magnon. Okay? So the Higgs particle, well, forget about the Higgs particle, I have no time. So what was mentioned, and I promised you to say a few words about the 1972 work of Volkov and Soroka. They noted, because supersymmetry is a fermionic symmetry, the effect of the spontaneous breaking of this fermionic symmetry would be the emergence of a massless fermion rather than a massless boson, Goldstone boson. At first, they even thought that neutrino might be such a fermion, might be explained by a spontaneous breaking of supersymmetry. But then they realized that that's not the case, and then they realized that if supersymmetry is spontaneously broken, the massless fermion of this spontaneous breaking can be coupled to gravitina, which is the superpartner to graviton. And due to this coupling, it makes gravitina massive. And that's very important to make it massive, because otherwise, if gravitina is massive, we would have a long-range force which is additive. I mean, the stars could emit pairs of gravitinas and could communicate with other stars. And of course, this is a weaker interaction than gravity, but it would be a long-range force. So I skip this and I skip this. Here is a single, this plot shows you a single argument, well, quote unquote empiric argument in favor of supersymmetry, but it's largely, rather than being fully empiric, it's largely aesthetic. But it uses experimental data. And the hope is, our hope today is that all these four distinct interactions which we have today, namely electroweak interaction, three electromagnetic, weak, and strong interaction, that in fact they unify at very large energies. Which means that if you introduce the running coupling constants, those which measure interactions at a given scale rather than just constants, which measure long-range interaction. You know, the running coupling constants were mentioned by Nick. If you measure the interactions, let's say the electromagnetic or weak or strong interactions, they unify at a given scale. At our scale, they are very different. Strong interaction is real strong, and weak interaction is real weak. But if you let them evolve to higher scales, they change. Strong interaction becomes weaker, weak interaction becomes stronger. Gravitational interaction also grows. And therefore, we hope, or many people hope, that, and this would be a great thing for aesthetical reasons, but there is a certain scale at which at least three known interactions they become equal to each other, and maybe even gravity becomes equal to this interaction somewhere here. So if you do it without supersymmetry, if you compare how the coupling constants run without supersymmetry, you get these yellow lines, and you see that they don't intersect at one point, and there is not real unification here. If you include superpartners, then the situation drastically changes. You see that this is 100 GeV, what we know, and this is, you see, 10 to the 15 GeV. This is a big mass gap here, but you see that with supersymmetry, all these three coupling unifies, and moreover, they become strong, and moreover, very close from this, just 3 orders of magnitude from this unification point, gravity also becomes strong, because the Planck mass is right here. So it is not included that somewhere here, all 4 known interactions become just 4 distinct manifestations of one and the same thing. So this is an aesthetic argument in favor of supersymmetry. And now in the remaining 15 minutes, as I said, there are no more experimental manifestations of it. We hope that they will be found at LHC, and there is very high probability they will. However, we should be ready to surprises. Surprises always happen. We are not gods. We cannot predict the future. We don't know what's going to happen beyond the interval of energy, which is already known. So in spite of big expectations, we should be ready to surprises. And in the remaining 15 minutes of my talk, I will briefly review a direction of supersymmetry, which is, of course, being a little bit less fundamental in nature, but where we already know that supersymmetry is extremely useful, and I will tell you a few facts about how it was used in order to make a significant progress, a significant advance. And again, as I said, Nick helped me a little bit because he introduced the notions of quarks and gluons and explained a little bit about what quantum chromodynamics is. This is a strong field theory describing strong interactions of quarks and gluons. Interactions are mediated by exchange of gluons, spin 1 gauge bosons. Gluons and quarks carry color charges, and there are two very special properties of QCD which are extremely counterintuitive. The first property, which was also mentioned by Nick, is asymptotic freedom. At short distances, the interaction becomes weaker, and this is counterintuitive because in all other theories we deal with, generically, the shorter the distance, the stronger the interaction. The shorter the distance between probe charges, the stronger the Coulomb interaction, the stronger the gravity interaction, and so on. But that's not the case with quarks and gluons. And another counterintuitive property, that hadrons are always white in the sense that they don't carry overall charge, because overall charge is always screened. There is, for instance, a representation of the free quarks and the proton. They all have different colors, and taken together, this is a white object, color singlet. And if you try to pull one of the quarks away, a linear potential between this quark and the rest of the proton appears and it won't let you to pull it away. This is totally, as I said, totally unlike QED, quantum electrodynamics. In quantum electrodynamics, if you have two probe charges, the force line of the electromagnetic field spread all over in space. And because of this, you have the Coulomb interaction, which falls like 1 over r at large distances, and there is no difficulty in ionizing objects, or pulling electron from positron at very large distances, because the potential is 1 over r, the force is 1 over r squared. Now, if you take in QCD a probe quark, heavy, let's say probe, non-dynamical heavy quark and anti-quark, and you start spreading them out, what you see, numerically what people see, is that a kind of a flux tube appears between them, and the larger you pull them apart, the longer is the flux tube, and you can never break it and pull one from another. This is a result of numeric simulation in a lattice. This is one quark, this is anti-quark, and you see they're at a certain distance. This is the density of energy between them. You see it's a flux tube-like. It's not like in QED it spreads all over. It's only forms a flux tube between it's like a rubber string between them, which the more you stretch it, the potential grows linearly. In this sense, we didn't know of such behavior, say, in the 19th century. It's a very new dynamical regime. Now the question is, are we aware of precedents of this dynamical regime? And before QCD, before 1973, when the confinement conjecture was formulated, we had only one in all the variety of dynamics. We are we know in nature. We have only one example of this type, and it's very kind of a little bit of a contrived example. And let me describe this example because, of course, everybody knows of this from school textbooks, but it is important because it sets the scene for the rest of for the remaining 10 minutes. Let's assume we have two long magnets, one magnet and another magnet, and then if we have just empty space between them, then we know what happens. There is the south pole of one magnet, there is the north pole of another magnet, and they interact, and as long as the distance between south and the north pole here is smaller than the length of the magnets, they interact with each other just like magnetic charges, just like the electric charges. Namely, there is a Coulomb law of attraction between them with the magnetic lines spreading all over, here and here. And if you try to pull them apart, the force between them will fall like 1 over r squared. Now let us change our setup and put sample here, and let's make it superconducting sample. There is a superconductor here. It's important that it's a superconductor of the second kind. There are two types of superconductors, first kind, second kind. This is a superconductor of the second kind, so we switch on our device. Then we know what happens. Cooper pairs condense inside the superconductors, and the question, what happens with the magnets? Okay, we know that superconductivity totally does not tolerate magnetic field. Magnetic field produces Cooper pair from condensation. On the other hand, the magnetic flux, which is emitted, let's say, from the south pole, it's conserved. The magnetic flux is conserved. It cannot just disappear, right? So there is a fight, a wrestling between two tendencies. One tendency is the conservation of the magnetic flux and the desire of the magnetic flux to spread from the south pole of one magnet to the north pole of another magnet. And another tendency is that superconducting medium doesn't want the magnetic flux to spread. Okay? So the compromise in this fight occurs as follows. The superconductivity is ruined, but it is ruined in as small spatial volume as possible. And all the magnetic flux, which used to be spread all over in space, in the case of no superconductor between, the superconductor squeezes it into a narrow tube. Inside the narrow tube, superconductivity is ruined, no Cooper pair condensate, and the entire magnetic flux goes from here to here through this tube. This is the magnetic flux tube, and this is the magnetic field. Okay? Now, it's clear that under the circumstances, if your magnets are inside the supermagnet, inside the superconducting sample, it doesn't matter how far they are from each other, because making them closer or further doesn't change the situation with the flux tube. The force between them stays constant, which means a linearly growing potential. If you have a huge sample of superconductor, you cannot separate these two magnets because this separation would require energy linearly growing with separation, so they are permanently confined in one sample until you switch your superconductor off. So this was the only known example. The fact that the magnetic field doesn't propagate inside, doesn't survive inside the superconductor is known as the Meissner effect, which was known from the 1930s. And but the formation of the flux tubes or vortices was theoretically predicted, as well as the existence of the superconductor of the second kind itself was predicted in 1955 by Abrikosov, and then it was within 5 years that these flux tubes were discovered experimentally. This was, I believe, the first of the second student paper of Abrikosov, and a few years ago he got the Nobel Prize for it. So it was a good student paper. But this is what is called now abelian flux tube. That is because we deal with electromagnetism. Electromagnetism is abelian field theory. It's U1. Now, to explain the fact that quarks cannot be taken out of the protons, cannot be separated, these three gentlemen put forward the hypothesis of the dual Meissner effect or non-abelian flux tubes in QCD. This is Mandelstam, Nambu, and Gerhardhoff. This was in the early to mid 1970s. And they conjectured that something of the type of the Abrikosov flux tube take place in the QCD vacuum. That the QCD vacuum itself, it's so complicated, it plays a role of a superconductor. But it is a more complicated superconductor because here we deal with the non-abelian fields rather than abelian fields. It's not U1 with a simple photon. We have to have interacting gluons instead. And moreover, the flux tubes which are formed in QCD are not the flux tubes of the magnetic field, because these are not spins of the quarks which interact. These are the flux tubes of the chromoelectric field. So Mandelstam, Nambu, and Hoff suggested that this Meissner effect has to be dual. Okay? What does it mean dual? If we replace everything electric by everything magnetic and vice versa, that's what is called electric-magnetic duality. Electric-magnetic duality is the property of quantum electrodynamics in the absence of sources. In the empty space, this is exact property of the Maxwell's laws. In the absence of sources are totally symmetric with respect to replacement of everything magnetic by everything electric. Okay? So these three gentlemen suggested that the QCD vacuum does have this property, supports the Meissner effect, and supports duality. This was a pure conjecture, a brilliant, very nice, elegant, I would say, theoretical conjecture, which was done, as I said, put forward in the mid-1970s. And since then, many, many people, you know, the best mind in the community in this area tried to quantify this conjecture to make it quantitative, at least in some sense. And for 20 years, there was no progress whatsoever in spite of enormous and vigorous efforts. So the progress, in a sense, came only in the first progress, or the first advance, happened 20 years later in 1994. It is due to Nathan Zyberg and Edward Wheaton, and it is entirely due to supersymmetry. Okay? That's where supersymmetry comes in. Without supersymmetry, what they did would have never been possible. Of course, now people went much further, but let me in few words say what they did. They considered a supersymmetric cousin of quantum chromodynamics. The theory they dealt with was not really QCD. It was a supersymmetrized version of QCD. So each particle was accompanied by a superpartner. Not only a supersymmetrized, it was not minimally supersymmetrized. Minimal supersymmetry in 4 dimensions has 4 supercharges. They used extended supersymmetry, which it's n equal 2 supersymmetry, which has 8 supercharges. So it is extremely supersymmetric theory, and it's clear now, in hindsight, it's clear why. The more supersymmetry, the more of a tool you have, the more power you have for solution of the strongly coupled problems. They considered SU2 gauge theory with SU2. Because of supersymmetry, SU2 is broken down to U1, and because SU2 is broken down to U1, the theory has magnetic monopoles, or the Dirac monopoles, if you wish. In this case, it's field theoretic monopoles, so they go under the name of the Hooft-Polyakov monopoles. Now, using the power of extended supersymmetry, they figured out that under certain values of parameters, monopoles, the interaction becomes very strong, because typically monopoles are very heavy, and you cannot go into the domain where they are light. But using extended supersymmetry, these two gentlemen managed to venture deep inside the strong coupling domain where the monopoles become light. And then they slightly deform this supersymmetry. This deformation causes forces monopoles to condense. And when the monopoles condense, electric flux tube U1 is broken and the electric flux tube is formed. So it is indeed a dual effect, because in the normal superconductivity, the Cooper pairs condense, and the Cooper pairs are just the charges, electric charges. So the electric charges are condensed and the magnetic flux tubes is formed. Here it's the other way around. It's the magnetic charges which are condensed, and then the electric flux tubes are formed. So it was an enormous breakthrough, at least if not in practical, in the conceptual sense, because this breakthrough demonstrated, A, that the dual Meissner effect might exist in nature, exists in fact in nature, at least in theories which are cousins of QCD. And second, that supersymmetry is an extremely powerful tool which allows us to explore the dynamical regimes which could have never been explored previously. Not a single precedent in the theory. Okay, so for the first few years, a feeling was quite euphoric. Indeed, I remember from 1994 to 1996 or 1997, all people in this area were absolutely happy all the time, day and night. A little bit of, but then it settled down a little bit. This euphoria faded away. And this basically happened in 1997, 3 years later, when Hanani, Zaffaroni, and Strassler showed that the flux tubes, was a beautiful advance, but they showed that the flux tubes, which are formed in this Seiberg-Witten solution, in fact are, in a sense, are our old acquaintances. They are abelian, and they are very much like the Abrikosov flux tubes. They occur in non-abelian theory, but their nature is purely abelian. Therefore, although it was a great demonstration of the possibilities of supersymmetry, it was not yet the element which would really bring us closer to the solution of QCD per se. And now in the remaining maybe -1 minute, this is my last by one transparency. I won't really go through this transparency in any detail. What I would say that from 1992 till present, in the 13 years that elapsed, there was even a significant further progress in this direction, and that the first thing to do in order to approach QCD per se, people had to discover non-abelian flux tubes. In non-abelian theories, non-abelian flux tubes. And this was eventually done by people listed here. Aouzzi et al., Roberto is here, and then Hanani and Tong. David is also, I think I see him. And we added a little bit with Alosha Jung. So by today, the non-abelian generalization of the abelian flux string is known. And moreover, I have no time. I wanted to go a little bit here, this part of transparency. I wanted to say a few words about my work with Alosha Jung, which dualizes this effect, but I have no time. I should say that I will just summarize it in a few words, that the first example, not in QCD, but again in supersymmetric theory, the first examples were obtained with the dual Meissner effect and non-abelian flux tubes rather than abelian flux tubes stretching between probed quark and anti-quark. So we are approaching the supersymmetry. Supersymmetry as a dynamical tool turned to be extremely valuable, and we are little by little we are approaching our final dream of complete understanding, or at least semi-quantitative or qualitative, but in part quantitative understanding of color confinement in QCD. So I have to few conclusions, very general. The first one, conclusions slash predictions. The first one is that most likely supersymmetry will be discovered at LHC. And if you ask my personal opinion, I would say that the odds are 80 against 20 or so. And the second conclusion, that irrespective of what is going to happen at LHC, supersymmetry-based methods prove to be extremely powerful in non-abelian gauge dynamics at strong coupling, and they will continue to grow and proliferate in the near future. Thank you.
What place in all this picture?
Yeah.
Scalar field.
Well, the scalar field is a we know, or we think we know of a single fundamental scalar field, which is the Higgs boson, which is not yet discovered, but everybody believes it will be discovered very soon. The Higgs boson appeared before supersymmetry, although not long before, but before supersymmetry, and it was introduced in the context of what is now known standard model. It's a boson which is responsible for the masses of all quarks, or the masses of W bosons, and the masses of other particles. So per se, the Higgs boson doesn't know about supersymmetry. However, supersymmetry in part proliferated and occupied such a dominant position because of the problem of the Higgs boson mass, and this is the most serious problem. The Higgs mass, we know indirectly, has to be in the ballpark of 150 GeV. Its natural value, and it's a mass of the scalar particle, so once you start drawing loops for it, they are quadratically divergent. And if you think that the theory remains more or less the same up to the Planck scale, its mass should be not 100 GeV, but 10 to the power 19 GeV, 17 orders of magnitude higher. Okay? So one of the primary goals of introduction of the supersymmetry, well, not introduction, because supersymmetry was before that, but one of the primary goals of supersymmetry in phenomenology, which grew in the 1980s, was stabilizing the Higgs mass if you have a supersymmetry, even if it is broken. Let's say supersymmetry is broken, the masses of all superpartners are 500 GeV, okay? Then the quadratic divergence of the Higgs mass will be cut off at 500 GeV, because above 500 GeV supersymmetry operates 100% efficiently, and all loops bosonic are cancelled against fermionic. And then the fact that the Higgs mass must be 100 GeV becomes, if not natural, but at least it's technically stable. If you put it by hand to be 100 GeV, it is not dragged by radiative correction to the Planck scale. Okay? So I would say that the Higgs particle played a very important role in the growth of supersymmetry as a phenomenological approach. Okay? On the other hand, once supersymmetry has grown, it predicts a number of spin zero particles, right, by itself, because let's say an electron has a selectron which has all other quantum numbers the same as electron, except for its spin is zero, and its mass is, because of breaking of supersymmetry, is expected to be a couple hundred GeV, and so on. A quark have quarks, and once they are introduced, of course, they start giving their contribution in loops, and there is a huge phenomenology on that. There was a question.
Oh, okay. Quick one, David.
Which is the most likely manifestation of SUSY that you think will be discovered at the LHC?
Well, there are a few ways. You know, there is no general consensus as to that. Because what we know generically from supersymmetry is that supersymmetry introduces superpartners, okay? And there are superpartners to quarks and superpartners to leptons. For instance, superpartners to quarks are quarks, superpartners to leptons are leptons. And everything depends very crucially on what is the lightest supersymmetric particle. It's called LSP. LSP is the lightest supersymmetric particle, and in most phenomenological model it is absolutely stable. In fact, it's the one of which they call dark matter SB. But in various models, LSP is different. In some models, these are, well, this is not universal statement. Depending on the pattern of masses of superpartners, most people believe that some squares, say stop will be discovered first. But some other people think that some other superpartners. In any way, it should be a cascade decays, because you have some spin 1/2 particle, which is a superpartner to something we know, and then it decays with various in a cascade which contains 3 or 4 links in this cascade, 3 or 4 decays, and there are lots of missing energy because some of the particles produced at every step of the cascade, they wait detection and they go away. So you see very unbalanced events, and with high momentum going in one direction and no momentum going to the other, no balancing momentum in the other direction. But this is not universal. You see, people are prepared to view many different to look at many different possibilities here.
We really have to stop now. I'm afraid this has been a fascinating discussion. Before we thank Misha and Nick again, we're going to start again at 5 to 4. That's giving us 15 minutes for tea. It's quite important that we get started actually as soon as possible. Can we thank Misha and Nick for 2 absolutely fascinating